All right. Here we go. Quick disclaimer. What I'm about to teach you is not inherently accurate, but it is a really good conceptual understanding. Okay. Remember in chemistry where they taught you how electrons would go around the nucleus like a planet goes around the sun? And then later they're like, oh, just kidding. It's really an electron cloud. It kind of is in that area. What I'm going to teach you today is the kind of like the planet model of electrons going around the nucleus. It's not accurate. It's not good. Like it's not true, but it gives you a really good understanding. And that's where we're going to leave it when you get to college. It falls apart. I'm not teaching you the math. There's a whole part of math here, but what I'm teaching you is what you need to know to be able to function with electricity in life at an everyday level. So, you're welcome. So, give that one a shot. Tell your neighbor.
It said that in the pre-quiz. So
It
was a question.
No, I know, but I think it's either A or B. So it's just A. I mean, what if I say B and then all goes wrong?
So at some point we do a lab quiz.
Yeah, right.
Sure. Do you want to do that now or do you want to do that later? Okay.
Yeah, I did.
Okay, correct answer is A is correct. You can think of it in terms of springs being connected, and they're being squished together. So, like here, they're like squished, like oh, and they want to go, okay. Versus here, it's like, yeah, they're not really comfortable, but they're not as squished as this. The springs aren't. Here, it's like versus. Does that make sense? Potential energy. There's more potential energy here. Okay. Okay, so in these diagrams, these dots are represent electrons, and their proximity towards each other is how squished they are. Does that make sense? Tell your neighbor what you think. Tell them why you think it.
No, that's not C.
Okay, correct answer is what I'm going for is B, 2. Why? Because there's more springs. They're equally squished together, but there's a total number more springs here than there is there. So there's more potential energy in this arrangement, this scenario, this object than that. You all right with that? So it's looking at the energy, looks at the total. Okay. Okay. Versus electric potential. Tell your neighbor. Correct answer is C. This is energy per electron. Okay. How crowded they are. Okay. So electric potential is how much electric potential energy there is per electron. Okay. How crowded, and that's determined by how crowded the electrons are. Good with that? Okay. Now this last thing, this is for those who are going to go on in physics. I'm never going to test this on you, but like a conceptual understanding, a correct conceptual understanding of electric potential. You know the relationship between electric field and electric force, where the electric field is the promise of an electric force. Like you walk into this region here, and where there's an electric field, and you'll experience a force. You have that same relationship between electric potential and electric potential energy. Electric potential is the promise of an electric potential energy. So in this region, there's a certain electric potential, and if you stick something with a charge in there, you'll have a certain amount of electric potential energy. That's all I'm going to hit with that. Just wanted to set the record straight, so that's what it really is, but there's a lot of math associated with that. Tell your neighbor. Correct answer is A. Object number 3. The electrons are super crowded together, like squished, so like, okay. There's a lot of energy per electron. They're really crowded. Okay. Okay, correct answer. Here's what I'm going for. B. So electric potential energy looks at the total amount of energy. That's your lab. You have your lab. And so here, even though the springs aren't that close together compared to this, or like the sheer number of them, at some point is going to have more energy here than this if you make it bigger and bigger and bigger, because just you add them up eventually, that's going to, thank you. You good with that? Good with that? Okay. All right. So, new term. I'll just let you know. 3 terms. They sound really close to the same thing. They are related. I apologize. I'd give it a different thing, but anyway, electric variable for electric potential is capital V. I think I put that in the video, right? Yeah. Okay. Electric potential difference is delta capital V. Okay, where it is the difference in electric potential. So mathematically, what are you doing? You're just subtracting them. And to keep it easy, we're just going to say it's the absolute value. So I don't care which one's 1 and 2. It's just the difference between the 2 spots. Okay. What would cause a greater electric potential difference to increase? This would be if there is a greater contrast in electron crowdedness from one spot, one point to another. If there's a greater contrast in electron crowdedness from one spot to the other. Good with that? All right. So 1 and 2 have the same crowdedness. 4 has the same crowdedness. 3 is different. I'm going to erase that and be still writing. Tell your neighbor.
It's kind of a confusing question.
Correct answer is? Correct answer is C. Okay. Here they're equal. Electric potential difference between here and here, but here it's not as cramped together in 3 as that it is in 1 and 2, so there's a bigger contrast. So greater electric potential difference from here to here than there is from here to here or here to there. Good with that? Okay, so now 1, 2, and 3 all have the same crowdedness, and 4 obviously same crowdedness. Tell your neighbor. There we go with D. Okay. I like D as well. All right. So, why do I care about dots and electron crowdedness? This electric potential difference, this concept is the single most important concept for this chapter, next chapter, and the chapter after that. Like this is like, you know how I taught you inertia, and that concept carried over throughout the rest of the semester. This is had like the electric potential difference is that important of a concept. Okay, so another name for electric potential difference is voltage. I'm assuming you've heard of that term. You probably don't know what it is, like you, or have an accurate understanding. I mean, some of you might, but most of the times when you use something, when you hear something used in just everyday life, it usually has some wrong conclusions. Okay, so today is like devoted to like getting you straight on what voltage is and what it is not. Okay, so another equation for electric potential difference is how much energy, electric potential energy, is transferred compared to how much charge or how many electrons are being transferred. Okay. Good with that, and we'll unpack that here. Good. Okay. So here's where this comes into like how does this impact my life? Okay. Voltage, electric potential difference, is to determine how motivated electrons are to transfer. Okay. So it's like looking at here, it's like electrons here, like, I want to get out, and they look over this region over here, and they're like, just as crowded, and like, man, I want to get out, but why would I want to go over there? It's just as crowded. There's no difference in electron crowdedness, so there's no motivation to go over to somewhere that's just as crowded. But if this region is crowded, but then over here, it's like, these guys are looking over there going, man, that would be awesome to get over there. And so they're really motivated. Does that make sense? The difference in electric potential, how crowded they are from one spot to the next, they're like, I want to get over there real bad. Okay? It's the motivation. Okay? Now, what determines if you live or die, how painful or powerful the shock is determined by how much energy is actually transferred. That's really important in terms of survival. Okay. So we should think about, what's going to cause this to increase, this electric potential energy to increase. So that equation I just introduced you to said how much energy, electric potential energy is being transferred for how much charge is being transferred. So let's just do that. So we could either increase the voltage or increase how many electrons transfer. How many electrons transfer? Does that make sense? The charge? Good with that? Okay. So this is where all these dots come into real life. Okay? And we'll look at some examples. Questions there? It's a really important slide right here. The concepts on here. You should probably pay attention and not be distracted. Multitasking is proven to be ineffective. Okay. Voltage is how motivated the electrons are to transfer. Electric potential energy determines how powerful the shock is, and we could increase that by increasing the voltage and or increasing the number of electrons that transfer. Okay. Tell your neighbor. Tell them why. Correct answer is C. There's a greater difference in electron crowdedness. Okay, so these electrons are way more motivated to jump over here than they are here or here. Okay, so if electrons were able to transfer, at what point would they stop transferring? Tell your neighbor.
I think I don't think it would transfer electrons.
Correct answer is B. Okay, until they're equally crowded. Okay, if this said electric potential difference is 0, then that would be correct. Okay, but electric potential is just, if electric potential is 0, that's when there's no crowdedness. Okay, they're going to go until they're equally crowded. Good with that? Okay, so 1 and 2 have the same crowdedness. Tell your neighbor what you think. Okay. Trying to come up with an analogy here. What do you think? Which one's going to get more powerful shock? Which one's going to have more electrons be able to transfer? So that makes sense. Like, they both have the same electric potential difference. Does that make sense? comparison of crowdedness is the same. So which one's going to allow more electrons to be transferred? What do you think? There's going to be more room. Here's my argument. Here, let's say 4 electrons are transferred out of here, and then they're like, okay, we're equally crowded. If we transferred 4 electrons here, there's still more room to make that until these both are equally crowded. Does that make sense? I'm trying to think of got a couple examples that are coming to me, but I don't know how good that. You guys ever played Chubby Bunny? You like shove marshmallows in your mouth or Chubby Bunny. Okay, so let's say they're like crowded. Which do you think? I don't know if this makes sense. Oh, which could you shove more marshmallows into when they're sort of crowded? A smaller mouth or a bigger mouth? And still be like you got more room to shove in a bigger mouth, or like what's something like if you ever made a pillow or like stuffing or like trying to think stuff that you like things that you shove in, like if you have a big pillow versus a small pillow, there's more, you have to put more stuffing in the big pillow to make it equally firm as a small pillow. Yeah, no. Okay, I don't know. Yeah, good. That's what I got. Okay, so does anybody know that? Okay, here's where all these dots come to like. Why does this matter to me? Like, when am I ever going to see dots in life? Okay, I tried really hard to make this pertinent to life. What is the voltage on an outlet? Depending on who you talk to, 110, 120. Okay, 120 volts. Okay, on a high voltage power line. Warning, high voltage. Those signs are usually, I've seen them from 5,000 to 20,000. Okay. The voltage on a Van de Graaff generator. I should have done this yet. When I turn this on, I'm estimating this, but it's around 1,000,000 volts. Like, why do you have that in my classroom? Like, that's gonna kill somebody. Okay, 1,000,000 volts. So what we're gonna do is try to figure out what voltage is and what it is not today. Okay, so if I am holding on to this cord that is plugged in to this outlet, am I safe from being shocked? Yes. Okay, we trust this rubber insulation all the time. Okay, it would be bad if this was frayed and you like had it, you could see the metal, like that would be like, ah, okay. We trust that this insulation protects us. Okay. Now, if I take a similar cord and I plug it into the Van de Graaff generator, take a cord. I take that cord, wait for it. Where'd I put that? There it is. Got it. And I plug that into take this. Why, I guess here's a first question. Why do I stand on insulation? Like the pink stuff. Why do I normally stand on that?
So it's not going to fly through you to the ground.
Yeah, it doesn't go through me to the ground. You okay with that? Okay. Now, what I'm going to do, actually, could you turn off the lights, please? Just press on the lower part of the switch. Yep. And then the other one. Perfect. Thank you. Okay. I'm going to turn this on, and you let me know if I am being prevented from being shocked. You guys see that? Did this insulation prevent me from being shocked? No. Okay, I was being shocked multiple times. Okay, why? Why am I not being protected? Because the voltage is so incredibly high. It looks at this insulation and goes, "Are you kidding me? You think that's going to stop me? Not a chance. I am so through this." The electrons are so crowded in here that they're able to jump through the insulation. That's what voltage does. Okay, you good with that? Now, a follow-up demonstration is, what do you think is going to happen if I take some steel wool and I allow it to be shocked by the Van der Graaf generator? Okay, so I've got a piece of steel wool here, and I'm going to turn this on. I'm going to hook it up across here. You all right with that? Okay. Okay. It's being shocked. You probably couldn't see it. It is being shocked, but it's fine. Okay. But if I took this same piece of steel wool, do not ever, ever do this at home. And I take this cord that is cut, I plug it into the outlet. That's the part that's super stupid. Okay. If I take this, actually, and I plug this into the outlet, and then I put this across the piece of iron wool. Okay. Don't look at the iron wool, steel wool. Look at my face. Okay. Do not look at the steel wool. Look at my face. Do not look at the steel wool. Look at my face. Ready? 3, 2, 1. Okay. Incinerated. Okay. So So the question is, how did that? All right. You might touch the ends of the wire. That's why. All right. So was I safe from being? I'm like recapping this demonstration. Was I safe from being shocked with the plug, the outlet? Yes. Lower voltage. Okay. That doesn't mean you should stick forks in your outlet. Okay. For the Van der Graaf generator, no. It had a very high voltage. Good with that? Versus did the steel wool get burnt with the Van der Graaf generator? No, because there was a limited supply of electrons transferred. Because there was a limited amount of electrons on the Van der Graaf generator, even even though they were very crowded. And was the steel wool burnt at the outlet? Yes, because there was an endless supply of electrons from the outlet. Van der Graaf generator had a really big electric potential difference, but there weren't that many electrons actually being transferred. And so there wasn't that much energy. Like you feel it, but it didn't destroy it. Versus an outlet had a lower electric potential, but the amount of charge was endless. And so that was what enabled enough energy to fry the steel wool. Okay, here's my analogy for that. Kuwait is a small country in the Middle East. It's oil rich. Most citizens in Kuwait are rich, like crazy rich, like a car per day of the week, rich. Okay, but the total amount of money that they're able to bring to the global economy is small. Does that make sense? Kuwait is like the Van der Graaf generator. Has a lot of energy per electron, has a lot of money per citizen, but total amount of energy, total amount of money isn't that much. The outlet is like China. Okay? There's a lot of people per person, they're poor. But if you look at the total amount, they're a huge factor in the global economy. There's that much money. They just don't have that much money per person, but they have that many people. They've got a lot of energy. Good with that? Okay, got a worksheet due tomorrow, test Thursday, so review due on Wednesday, like the normal regime.